we've talked about the fact that when you take two individual protons and two individual neutrons that are separated by a large distance, and you put them together to make a helium nucleus, okay, we know that this is in a lower energy state, okay? This has less potential energy than the original four nucleons when they were individually separated from one another. So when you put the four of them together into a helium nucleus, they're in a lower energy state and they have less potential energy. Okay, and if you think about that, if that's the case, then when this happens, okay, well, maybe we'll come back to that in a second. Okay, all right. Now, what we find is this. Okay, if we're going to now look at a helium nucleus. Okay, we've been talking about a helium nucleus. Let's actually look at it. So here is information that we're going to need in order to analyze the helium nucleus. All right, so what we're going to do is, with the data in this table here, we're going to try and calculate the mass of two protons and two neutrons and compare that with the mass of a helium nucleus, which, as we know, is two protons and two neutrons. Okay, and we're going to find something interesting here. Now, before we do this, we need to know something about this unit here, U. It's called the Unified Atomic Mass Unit, or atomic mass units. And what you need to know is that that 1U, in fact, I'll leave that there. What you need to know is that 1U is equal to 1.66 times 10 to the minus 27 kilograms. Okay, 1U is 1.66 times 10 to the minus 27 kilograms. The unified atomic mass unit is defined as exactly 1/12 of the mass of one atom of carbon-12. Okay, now one atom of carbon-12 has a mass of 12U, so a twelfth of that is 1U. So the unified atomic mass unit is 1/12 of the mass of one atom of carbon-12. That's its definition. And all you need to know is that 1U is equal to 1.66 times 10 to the minus 27 kilograms. You'll find that conversion in the data booklet. Okay, so we know that a helium nucleus is two protons and two neutrons. So we're going to calculate the mass of the individual nucleons, okay? So mass of two protons and two neutrons. That's what we're going to calculate here. So we're going to do 2 times 1.00728U, because that's the mass of a proton, plus 2 times 1.008666U, because that's the mass of a neutron in unified atomic mass units. Okay. Now, if you do this calculation, what you'll find is you get this: 2 times 1.00728, okay, plus 2 times 1.00866 gives you 4.03188U. Now, we know that the mass of a helium nucleus, the mass equals 4.00151U. So immediately it should be apparent there's something funny going on here. The mass of two protons and two neutrons is greater than the mass of a helium nucleus. Okay, so what we find is that this is the mass of four individual nucleons, two protons and two neutrons, when they're separated from one another, and they're not bound to one another, they're just individual. And this is the mass of those same four nucleons when they're joined into a helium nucleus. So it appears that they've lost some mass. Okay, and indeed they have. Now, we can explain this, though. It's very puzzling initially to scientists, this, but we can explain this because the great physicist Albert Einstein, in his work on special relativity, which he completed in the early 1900s, and it's probably his most famous work, but it's not what he won the Nobel Prize for. He actually won the Nobel Prize for explaining the photoelectric effect. But anyway, that's beside the point. The work of Albert Einstein on special relativity led to this equation: E equals mc squared. Most famous equation probably in all of physics. Probably even more famous than Newton's laws. Okay, now this equation here helps us with the problem that we've got. So let's look at that equation first. Now the equation, if you look at it, okay, E equals mc squared. E stands for energy, and importantly that's in joules. M is mass, and that's in kilograms. And c is velocity of light, or the speed of light in a vacuum or in air, which is about 3 times 10 to the 8 meters per second. It's not quite that in air, but it's very, very close. Okay, and if you round it to 2 decimal places, it's 3 times 10 to the 8 meters per second. So E equals mc squared. Energy is equal to mass times the speed of light squared. Now, what's Einstein saying in this equation? What does it mean? Well, what he was saying is he found that energy and mass are equivalent. Okay, so when we talk about the conservation of energy, that energy can't be created or destroyed, actually it should be the conservation of mass energy, because energy can't be created or destroyed, but it can be converted into mass. Mass and energy are equivalent. Okay, so what's going on here? Where's this missing energy going? Well, the answer is, where's this missing mass going? Okay, because the mass of the nucleus is less than the mass of its constituent parts. Well, that missing mass is turning into energy. Okay, so when we put these 4 nucleons together, they combine, okay, and they enter a lower energy state. They've got less potential energy than they had before. So if they've got less potential energy, they must have given out some energy, and indeed they do. Okay, so when these 4 nucleons combine together to make this nucleus, you get the nucleus plus some energy. Okay, and that energy there usually becomes the kinetic energy of the nucleus. Okay, the nucleus will sort of fly off or whatever. All right, now that kinetic energy, so this is usually kinetic energy, but we'll just say energy. That energy that's released has been converted from mass. Okay, so when you put the nucleons together, they lose energy. Okay, and they give that energy out. Now, where does that energy come from? It's been converted from their mass. Okay, so they've lost mass, but that mass has been converted into energy. Energy and mass are equivalent. Okay, so that's what we're saying here. All right. The energy that's given out by these nucleons when they join together into a combined nucleus results in, I suppose you could say, a decrease in the mass of the nucleus. Okay, the difference between this mass and this mass, okay, is the m in this equation. If you multiply that by the speed of light squared, you get the energy that is released. Okay, and this is fundamental nuclear physics, which is used to explain nuclear reactions, nuclear energy, nuclear fusion, nuclear fission. All right, and this was first really explored in sort of the early 1930s. The first time that a nucleus was split. Okay, splitting of the atom was 1932 by 2 scientists called Cockcroft and Walton, and there's some information about that in the PowerPoint. You don't need to know it for the exam, but I think it's interesting, so I've put it in there. And then in 1938, Otto Hahn and Fritz Strassmann actually discovered nuclear fission and carried that out for the first time in 1938. Okay, so that's how the history goes.